All right. Let's give people just a few moments to kind of drop on in. Give them a chance to catch up. You know, I really think I ought to get some kind of a opening video sequence here. We're going to create a little bit of a video experience in order to try to get people in the mood to try to get this all technical art chutzpah up and going. Okay. Well, I think we're going. I think we're still live. We've been going on for 30 seconds, so that should be good enough for everyone to drop in. So let's get this show on the road. Welcome, tech artists from around the world. It's Friday, it's 12:30, so that means it's time for another episode of Tech Art Talk Live. My name is Chris, and I will be your host for today. Now, for the last couple weeks, we've been talking about things related with visual effects. We started off with an introduction a couple weeks ago. Last week we did a kind of coverage of in-camera effects and post-processing. And now we're getting to go on, before we go on to the other types of effects, I can't believe that I really have forgotten about this. We're just about approaching a year now that Tech Art Talk Live has been going on. I have not yet once given a lecture or talk about this particular topic, and it's so freaking important. It was a mental schism. It just never dawned on me. And so today is the day. What we're going to be talking about today is the real-time rendering pipeline, which is really so important. And it really has everything to do with visual effects, because visual effects, in my humble opinion, is really just the exploitation and the manipulation of the real-time rendering pipeline. Every kind of visual effect, whether you go from a post-process all the way down to a simulation and through particles, are manipulations of the rendering pipeline. And you got to know what the rendering pipeline is in order to create your visual effects. So we're kind of like taking a little bit of a backward step today. We're going to go over what is the real-time rendering pipeline. Now, in order to really understand this stuff, you really got to get out there and get programming with it and start, getting your hands dirty with it. However, this is going to act as kind of a primer, just kind of like act as a bit of a kind of a reminder on how everything goes. Some of this you might have seen before, and a lot of it you haven't. But hopefully with this, you'll understand what is the real-time rendering pipeline. So let's get things started with the real-time rendering pipeline. Yes, sir, Bob. Okay. So let's see. So really, a lot of people might be scratching their noggins going, all right, Chris, what is the rendering pipeline? Okay, it's a group of operations that all visual assets must pass through in order to get displayed in the game. Every little thing that goes and displays to the screen has to go through this rendering pipeline. Now, each rendering engine has its own specific variation of the rendering pipeline, but they all have the same behaviors. It's kind of like an engine. An engine has a combustion chamber, and the combustion chamber rotates and it turns a crankshaft, and the crankshaft goes ahead and maybe even interacts with a transmission, and the transmission gets put rotation into the wheels. Okay, every single vehicle, every single engine has those same things. And just what I'm going to go through, every single rendering engine has these particular elements associated with them. And we're going to go through them today. And that means we're dealing with characters, props, environments, visual effects, you name it. It all has to go through the rendering pipeline. Now, the cool thing about the rendering pipeline, just like automobile engines, and this is one of the reasons I think why I love hot rodding so much, is because it's a good allegory for the rendering pipeline, because it's extraordinarily customizable. Almost every stage along the way is manipulatable. And in my opinion, I call the art of visual effects is the manipulation and exploitation of any and all stages of the rendering pipeline. That's kind of like my idea. All right. Now, just as in the automotive hot rod world, no two engines are the same. Well, guess what, gang? No two rendering engines are the same either. Okay, and I wish I had a quarter for every artist that's come up to me with, a frantic look on their eyes, and they say, well, why doesn't it look like my scene in Maya? It looks great on my machine. And then suddenly I give it to my producer, I give it to my level designer, and they put it in game, and it looks like donkey poop. What's going on? Okay, the reason why that is because there's a real-time rendering pipeline that you're developing your current game or your current experience on. And then there is the rendering pipeline that your DCC is on. Those are two different rendering pipelines. And guess what, gang? They don't talk the same language. Well, they kind of talk the same language, but they don't behave the same. They look different from each other. They eat different things. Yeah, it means that they consume data in a different way. And they have different results, obviously, because people are going to complain, hey, it looks great in Maya. Why doesn't it look good in real time? Now, an allegory of that is if you can compare NASCAR engines with Formula One engines. NASCARs, those are the hot rods that they love them in North Carolina, and they go around in a great big circle or a square oval or a round track, and they go around and round and round and round. And Formula Ones are the hot things that they race in Italy, and they go around the corners and zip around, and they go really, really fast, and they're all driven by a guy named Luigi. And so that's a big difference. But other than that, a NASCAR engine and a Formula One engine are entirely different things, even though there are race cars. They both essentially do the same thing, but they do them in radically different ways. In the exact same way, no two rendering engines are exactly the same. All right. Now, there are two major pipelines that most rendering engines kind of conform with. Actually, kind of three if you count the third one here. So the first one is the Direct 3D. And this was generated by Microsoft. And they created a language called HLSL. And the HLSL language is actually becoming more of an ecumenical kind of like industry standard. And but really, when you're talking about Direct 3D or DirectX, that's a Microsoft project. Then we have the Open Standard or OpenGL standard, which is more part of the public domain, and it's open source. It's monitored by the Kronos folks, and they have a language called GLSL. Okay, gang. HLSL and GLSL are practically like the same language. They're like almost like brothers, or they're like cousins of each other. Like they're every single element they have in one can be found in the other, and it's really just kind of like a reorganization of the data a little bit. But other than that, they are exactly like the same language, and they are. And there's really, for the uninitiated, it's really hard to tell the two apart because they look so close to each other. Okay, now the OpenGL is evolving into something called Vulkan, which is kind of like really more of an open standard. And I believe, I'm not sure about this, and now some of you folks, please chime in, but I believe Vulkan can support either an HLSL or a GSL standard kind of language, because it's really all about the central API supporting the underneath of it. So I believe everything is kind of like shifting more towards the OpenGL, and whether you speak in HLSL or GLSL is really just a matter of preference, because they really are practically the same thing. And now on the third side of things, there's also Metal, which is the Apple product. Apple, has got to be different, and they've got to, do things on their own, and they've got to do things better, and they have their own graphics language, and it's called Metal. And I don't really know much about it because I don't know a lot of hardcore graphic 3D renderers working in Metal. Now they do exist, but they're just not that prevalent around. But it's something to consider if one was wanting to go into and study more of the graphics pipeline for Apples. Well, you're going to have to study in Metal. Okay. Now, there are 7 stages to the rendering pipeline, but it begins all, like if you check it out on the far left-hand side, you got the vertex or the index buffer, and it ends all the way up to the frame buffer. So we're going to start off in the vertex buffer, and then we're going to pass, and that basically the vertex or the index buffer is a big bank of information where the computer is going, okay, I've got a buttload of stuff to render. Here it is. It's a great big buffer of inner stuff. And what does it do with it? It puts it into the first stage, of what's called the input assembler. Now the input assembler just kind of organizes all of the vertices and so forth. And actually, let me just go right through this. Let me talk about every one of these stages real quick, and then I'll go into them in greater detail. So the first is the input assembler stage. The second is the Vertex Shader stage. Now this one is a programmable stage. This is fully programmable with the input assembler. It's configurable, but you couldn't really program inside of it. The next is the tessellation stage. Now the tessellation stage is programmable as well. And this is likewise the geometry shader. The geometry shader actually can add or subtract more information to the detail than what was there originally. Now this can be programmed as well. Then the next stage is the rasterization stage. Now actually this is the telltale heart of the entire rendering pipeline. It all comes down to this. In fact, a lot of folks call the modern rendering pipeline, or this particular pipeline I'm talking about, the rasterization pipeline, because all about this step. And this is where it translates the 3D into a 2D bitmap, or a 2D, a bitmap, exactly. And then you go on to the fragment or the pixel shader, and where the thing gets rendered, and then we have to go on to the color blending stage, in which all of the individual layers of all the individual objects that were rendered get loaded up and blended on top of each other, and then they get passed on to the final frame buffer. All right, so let's go ahead and go to every one of these stages and describe what each of these does. Okay, the input assembler really just is kind of like the funnel that kind of grabs all the stuff and kind of organizes it. And really all it's organizing is a bunch of vertices. And so it assembles the data into vertices and to primitives. And it may use something called an index buffer. An index buffer is a little bit a way of organizing the data in such a way so that you can repeat multiple vertexes multiple times without actually having to incur the cost of the memory associated with it. And it breaks it up into primitives, and there are 6 different primitives that the input assembler can actually input or consume. And the first is a point list, which is literally just a list of vertices. 0, 1, 2, 3, you have it. And then you have a line list, and then it's just associated with a line is nothing but 2 points. I've got point 1 and point 2. There's a line. Point 3, point 4. Now there's a line. Now, and that's how it goes through, and it digests all of the data according to those little lines. Now we have a line strip. A line strip automatically assumes that the last point appends to the previous point, and it just extends the line just a little bit further. So I have point 0 and point 1. Okay, that part's part of the line. Point 2 is the second segment. Point 3 establishes the third segment, and so forth. And so the strip just keeps on adding more and more and more and more to the line. Okay, so that is kind of like kind of like one-dimensional direction. What about two-dimensional? Then you have things like called a triangle list, and that's where you have 3 different points, and that establishes a triangle. 0, 1, 2. Okay, there's the triangle. 3, 4, 5. There's another triangle. And likewise, like a line strip, a triangle list is a group of triangles, and it's created in such a way. So we go 0, 1, and 2. Okay, there's a triangle. I put in point number 3. Now that creates a new triangle that goes 1, 2, and 3. And then we're going to add one more vertex, vertex 4, and that's going to go 2, 3, and 4. Another vertex, and that is 3, 4, and 5. As you can see, it just keeps on for every point that you add, it adds one more triangle to the entire list. And so that's what's called is a triangle list. Now, did I say that there were 6 primitives? Okay. Now, actually, there are a lot more because there are also considerations taken according to adjacencies. But these 5 are the primary primitive type lists that any kind of real engine kind of goes in. In fact, most of the time, you're dealing with triangle lists. Now, when you're dealing with certain visual effects, you might be dealing with some line lists, or maybe some triangle lists, or maybe even points when you're rendering particles. But really, most of the time, when you're rendering just on a non-visual effects basis, you're pretty much dealing with just triangle lists. Okay, We go on to the next stage, which is the Vertex Shader. Now the Vertex Shader is, it gets the information from the input assembler and then it passes it and it does a process. And it is a small programmable function. That means that this is a stage that is fully programmable and is performed on this, kind of like this function is performed on every single vertex. And what it does, what it's got to do, this is the only kind of obligation that the Vertex Shader has to accomplish. It transforms the vertex from object space to screen space. Now, a lot of you folks might be scratching your noggin. What do you mean the transforms from object space to screen space? Okay, in other words, we're working with a object that is set here, and it's go from 0 to 1 space and X, Y, Z. Okay, we're modeling it, that's cool. But how does that work into the screen space, which is a flat 2D screen? Well, anyway, the Vertex Shader transforms my object that I was working on my desk. It was looking pretty cool, and it transforms it into such a way that it looks proper on the screen. So that's what the Vertex Shader does. And this is really the only essential stage of the rendering pipeline. We can pretty much waffle or kind of like pass through, ignoring almost every other stage, but the Vertex Shader is the only real essential component, or the only real essential stage that has to happen. Okay, next is the tessellation stage. Now the purpose of the tessellation stage is to subdivide each surface. And that means is it doesn't add any more geometry, it just takes the geometry and just starts subdividing it. And this does improve mesh quality, and you could create dynamic LODs. What that means is that suppose you have your object and it is close to the camera and far away from the camera, and it does this great big dolly in and forth. Okay, so it might go through a bunch of LODs, but instead of actually modeling all the LODs, what you can do is actually have the geometry tessellate dynamically according to the distance to the camera. And so therefore, the further it is, then the lower the level of detail, and the closer the camera gets to the object, then the higher level of detail. So that's really cool. And this is the first of the optional programming stages. You know, you don't have to do it, but this is available. Okay, so this is an example of what tessellation looks like. Now, if you can start off with a sphere. A sphere in its most primitive LOD is really just a cube. And then we go, if we were to use Catmull-Clark subdivision, we do one subdivision, and that sphere turns into something that starts to look a little bit more like a sphere. We go into 2 subdivisions, and it starts to get rounder and rounder, 3 subdivisions, and so forth, until you get to 6 subdivisions, and you're talking with a pretty darn smooth bowling ball. And so it doesn't take a whole lot. And guess what, folks? This is absolutely free. It means it comes with the engine. Your modelers don't have to model all this stuff. The engine is doing all this subdivision for you, and that's what tessellation is. Then we go on to the 4th stage, which is the geometry shader. Now the geometry shader actually does add more geometry. You can add more vertices, you can add more points, you can add more polygons, or you can take them away. And this geometry shader is performed on every single primitive. In other words, every single triangle, every single line, or every single vertex, if it's a unique entity or a unique primitive, then it performs this information on. And that is whether it's a triangle, line, or a point. Now, this also is an optional stage. Now, as I said before, it can or cannot, or it can add more geometry to the scene, or it can remove geometry. And the down parts of this is that it tends to be kind of slow. So at this moment in time in rendering history, the geometry shaders are not terribly popular with the shading crowd. You know, they're not terribly in vogue. Maybe they'll have their heyday, maybe they won't, but it is possible and it is available, and it's extraordinarily popular, or powerful, I'm sorry. Now the 5th stage, this is the rasterization stage. Now this is where the 3D image is transformed into a 2D bitmap, a 2D raster image, in other words. And so it knows where the screen resolution that it has to conform with, and that basically the rasterization, all it's doing is identifying which pixels or which fragments are meant to be rendered. It doesn't actually render them. It just identifies which ones of these pixels are actually going to be rendered. And it looks kind of something like this. I picked this image off of the internet. If you have the viewer is looking at the screen, and you'll see that it kind of creates a little pyramid from the viewer to the object that you're viewing. And so wherever that pyramid intersects the screen, it highlights or turns on those pixels that are intended to be rendered. Okay, it's a pretty cool algorithm. It's pretty fast, and they put this right onto the chip, and it goes really, really fast. And this is like one of the reasons why you can render millions of polygons all at once, is because it zips right through this rasterization stage. Now, you might want to say, okay, what about all this detail? I spent all my time putting my vertex colors, I have UV information, they have normal map information. So what does it do about that? Okay, it does something called bilinear interpolation between the pixels of the bitmap. So therefore, remember that we are dealing with triangles. And so each of those triangles has a vertex on each of the corners of those triangles. And each one of those vertices has things like the vertex color, the UV information, and a normal map, whatever. And they use a process called bilinear interpolation to interpolate all of the pixels in between all of those vertices. And that's where the pixels actually inherit all of the data that is coming from each of their relative vertices using bilinear interpolation. Okay, here's the pixel or the fragment shader. Now this is the stage that most people associate with as being the rendering stage, but actually this is actually the 6th stage, and it's actually just one of the stages. And this is where it is, believe it or not, technically optional. You don't have to have a pixel or fragment shader. An example of this is shadow maps. Everyone's heard of shadow maps. Shadow maps is how a real-time rendering engine creates shadows, right? And they are little baby texture maps. Well, these little baby texture maps get created, believe it or not, inside of the vertex shader. They don't happen in the pixel shader. In fact, it totally just ignores the pixel shader. And it happens in the vertex shader. And so technically, the fragment or the pixel shader is optional. But in other words, this is where the program is run on every single pixel, and it decides what color to make every one of these pixels. And so it decides that, okay, well, we're going to color this pixel, or we're going to color it green, we're going to color this pixel, we want this kind of a color of magenta, or what have you. But anyway, this is a little baby script. Well, actually, I shouldn't say baby. Daggone, I've seen some pretty huge pixel shaders before, and they can be pretty powerful, especially when you start getting into something called ray marching. What is ray marching? It's something to look forward to in a future Tech Art Talk Live. It's a bitchin'ly way cool thing to do with your pixel shader. It's like putting a genie inside of the pixel shader box, basically opening up the entire world inside of the pixel shader. We'll have to go into that in a little bit later. Stay tuned for that. But anyway, this is programmable, and when people start talking about PBR, or physically based rendering, it all happens here inside of the pixel shader. Now, there are other influences, but whether it is a PBR or a non-PBR shader, it still uses the same 7 stages. However, this is where those impacts are really fine, and then this is where the rendering formula goes. Now, we went over the rendering formula, maybe about half a year ago. Anyway, this is where it's implemented, and this is typically where what you have heard of as the blend Phong or shading algorithm happens. Now, this all happens here, right here in the fragment or the pixel shader. So this is the one that gets all of the star. This is really the star of the show, but it is by no means not the most important. All right, once all of the layers have been rendered, all the groups of polygons have been rendered for each of the shaders, then all of the layers that they were rendered to get, kind of like layered on top of each other. And then they're just sitting there in virtual memory. The color blending stage tells the pipeline how to render or how to layer each one of these things, and it tells the pipeline how to stack them up all on top of each other. And so this is the last phase of things, as it puts all of each of the rendered rendered materials all produce one specific layer, and then the color blending gets all these layers and smashes them all together, and it uses kind of an algorithm that goes from the furthest from the camera to the closest. So it lays down this layer, lays down that layer, lays down that layer, that layer, in a piecewise manner until it eventually all flattens out. Okay, now believe it or not, this sounds like a complicated operation, but it's actually pretty simple, meaning that there are only so many ways of combining pixels with each other. And so therefore it is non-programmable, as all of these states have been pre-initialized into the rendering chip. And so it uses something called depth testing or stencil testing, where it uses information in the depth buffer in order to realize, all right, sometimes some of these layers, they might intersect each other, and some of them might go through. And so it uses these algorithms called depth testing and stencil testing in order to figure out which pixels are actually occluding each other in order to help organize each other. Now, those are a little complicated algorithms, and people used to get their PhDs in that kind of stuff, but it's a little bit out of scope for our current Tech Art Talk presentations. But just know that they're there, and the color and the blending is the last stage of where it collapses all of the rendered images together into one big old image. It gets passed on to the frame buffer, and it gets passed on to the display. Okay, now is this the final and end all of the rendering pipelines? Maybe. Maybe yes, maybe no. It's really hard to say. Okay, guess what, gang? Right now, this is the rasterizing rendering pipeline, remember? Okay, there is another thing coming down the pipe, which is kind of revolutionary. Well, it's not ever actually revolutionary, it's actually kind of ancient, but it's only just now becoming real time, and that thing, my folks, is called ray tracing. Now, you probably have heard of ray tracing before. I've given a couple lectures on it before. I'm super duper excited about it, and the rendering pipeline does not look like the rasterizing pipeline. It is a little bit different. Actually, it's radically different. And so what it means is, right now, this modern rendering, the rasterizing pipeline, it's going to be around for at least a good 5-10 years. But what it's going to get replaced with is the ray tracing pipeline. So you're probably asking, well, if the ray tracing pipeline is going to be so good and it's going to replace the rasterizing pipeline, should I even bother learning about the rasterizing pipeline? And the answer is yes. You got to learn about it, folks, because the ray tracing is not here yet. It's coming, and it's going to come relatively slow, because right now the real-time rendering, it's still very, very demanding, and it's still super duper expensive, and you got to get yourself like a red hot NVIDIA card in order to handle it. So this is by all means a standard, and it's certainly no way it's going to get a ray tracer, real-time ray tracer, to fit inside of your iPhone. No way it's going to make the iPhone melt. So it's going to be a while until ray tracing becomes the standard. And what are you going to do until then? You're still going to create your visual effects, right? You got to create your visual effects in the context of the rasterizing pipeline in order to keep going. So yes, the modern rasterizing real-time rendering pipeline is the standard, and it will be the standard probably for at least 5 to 10 more years, and it'll take a bit of time for the ray tracing pipeline to actually get it. And some folks just plain don't like ray tracing. They would rather have rasterizing. And so I don't think the rasterizing pipeline is ever going to go away totally, because I think that it'll be a stylistic choice whether they want it rasterized or ray traced, and people will juggle in between. Okay, so it will be truly a choice of whether you want to use a wrench or use pliers in order to get the job done. It's just a different tool doing the same thing. Okay, that's what I wanted to present to you folks today. Check us out next week. Now next week, that's 707. No, that's July. Okay, 5/7, should say. That's May 7th. Blonde hair moment there, I guess. Anyway, join us again on May 7th. And then we're going to go back onto the visual effects king, and we're going to start dealing with immaterial effects. Now, immaterial effects takes advantage of all the stages of the rendering pipeline, and you can manipulate them all in the material. And this is why I wanted to definitely make sure to go through today's lecture here, because otherwise you're going to have no idea what I'm talking about next week when we go into the immaterial effects. All right, now if you like what you saw today, go ahead and subscribe on the little lower, what is that, the lower left hand, the lower right hand corner. Go ahead and subscribe to me. Join us, and you'll get informed whenever we start to go live. Now check us out on this channel on YouTube, or even better, go check me out, Chris Rhoda, on Facebook and on LinkedIn, or check out Art EDU, which is kind of like the big umbrella organization that kind of encompasses this whole thing, also on Facebook and on LinkedIn. All right, now if you really want to help me, go to the techartedu.com website and go ahead and opt in to our subscriptions. Go ahead and press the little click here now. You're going to give me your email address, and then I will make sure that you get informed to all this. And I've been promising updates, and I have been neglecting it, and that is because I've been very bad, because I've been working steadily on getting the real-time visual effects for the technical artists out the door. We're getting there. We've got the first draft finished, working with reviewers, making the text sound like it was written by an educated human being, and I'm also working on with the artists, making lots of pretty pictures for it. It's on its way, and it's really coming, and we're only about 7-8 months late on it. Yes. Okay. But that's the reason why I haven't been updating it, but we will continue to update stuff, so be patient. All right. Thank you very much for all of your attention. Thank you very much for coming today, and we'll see you all again next Friday, May 7th, where we're going to be talking about the in-material visual effects. And until then, bye.